The word atom was an empty promise from the start. In ancient Greek, it means uncuttable, but scientists cut it anyway. Think of physical matter like a set of wooden Russian nesting dolls. You open the outside doll, a wooden table or a glass of water, and you find molecules. Open the molecules and you find atoms. Open the atom and you find protons, neutrons, and electrons. For a long time, that seemed like the end of the line, but physicists wanted to look deeper. To see if the proton was truly a solid brick, they used the exact same strategy pioneered by Ernest Rutherford earlier in the century, shooting tiny particles directly at it. By the second half of the 20th century, laboratories were still using that approach, but they required larger, more powerful machines to generate enough force to crack a proton open. When those high-energy collisions finally happened, the incoming projectile scattered. They bounced off as if they were hitting hard pits buried deep inside. The proton was not a solid sphere. Every proton has exactly 3 distinct pieces inside it. Neutrons have 3 too. Physicists gave these tiny fragments a strangely poetic name borrowed from a novel, quarks. So the proton, the piece of matter once taught as the ultimate foundation of our universe, is actually just another wooden container hiding smaller secrets inside. The electron, on the other hand, is a different story. Despite every attempt to break it apart, laboratories have found no internal structure. As far as we can tell, it is a truly fundamental point in space. That particular doll refuses to open. But back inside the proton, those 3 quarks follow a bizarre set of physical rules. Usually, forces like gravity or magnetism get weaker the further apart objects drift. The strong force holding quarks together does the exact opposite. It acts like a microscopic elastic. The harder you try to pull 2 quarks apart, the more violently that band stretches and pulls them back together. Because of this rule, nature prevents a single quark from ever being isolated from its group. If you keep pulling with extreme amounts of energy, the bond still doesn't snap. Instead, all that accumulated energy transforms into new physical mass, instantly materializing into brand new quarks at the severed ends. It is a lot like trying to cut a bar magnet in half to separate the North Pole from the South. You never get an isolated pole. You just end up holding 2 smaller, fully functioning magnets. Because this intense energy converts into mass to heal the broken bond, no laboratory in the world will ever possess a solitary quark. They exist solely in groups. There is a second strange reality down at this microscopic level, and it changes how we measure our own physical weight. If you look at this balance scale comparing a whole proton to its 3 internal quarks, the numbers don't add up. The physical mass of those 3 tiny pieces is roughly 1% of the proton's weight. The remaining 99% is confined energy, the furious agitation of quarks and binding fields. That energy weighs down the scale. Now, take that math and step onto a standard bathroom scale. Almost every single ounce of your body weight comes directly from the heavy nuclei of your atoms, the protons and neutrons. That number on the scale represents the trapped, furious energy buzzing inside every atom of your body. You are made of imprisoned movement. The ultimate lesson here is that, in science, a fundamental particle is only a temporary title until someone builds a better machine. And there is one tiny piece we haven't opened yet, one that is passing through your body by the billions this very second, the ghost particle.